Hello Chem 1B, this is chapter 15, lecture video 5, and we're going to be discussing, at least in the beginning of this video, the 5% rule. So sometimes it's not necessary to do the quadratic equation, and that's what the 5% rule is all about. It's an approximation that allows us to assume something about our reaction that I'll discuss in a second to eliminate the need to do the quadratic formula and solve a quadratic equation. Now, sometimes it just makes sense to use the 5% rule because it makes the calculation a lot easier, and approximately we get pretty much the same answer whether we do the quadratic or whether we use this shortcut. But if you always want to do a quadratic equation, you will always get the correct answer. The 5% rule is just kind of a shortcut to the process. So it's very useful, and we're going to see that it's incredibly useful in the next couple chapters that we cover, because a lot of acid-base reactions are totally allowed to use the 5% rule, so it just makes calculations much faster. So let's look at a situation where we might be able to use the 5% rule. And mostly the beginning of the problem is going to be exactly the same as what we saw in lecture video 4, the last lecture video. So let's I'll tell you when we can start doing a difference in solution, right? So we have this balanced chemical equation, it's an equilibrium, and we're told that the initial concentration of acetic acid, which is this guy right here, is 0.1 molar. We know the equilibrium constant for this reaction, KEQ, right, is 1.8 times 10 to the negative 5. So we want to know what are the concentration of the products at equilibrium effectively, right? So first step, as always, is going to be setting up an ice table. We know our initial concentration of the acetic acid, right, this guy, is 0.1 molar. We know that we do not care about water because water is a pure liquid, which means we can ignore it in our equilibrium calculations. We weren't given any initial concentrations for our products, so again, we're going to be assuming that they're 0. And at this point, we don't know any equilibrium conditions, so we got to use x for our change and put everything in terms of x, right? So we know our change in acetic acid is going to be minus x. The change in the products is going to be plus x because we have 0 of them initially, so we have to shift towards the right side of this equation when we're doing this problem. We add the two rows, right? We get 0.1 minus x is our equilibrium condition for acetic acid, and x for acetate and H3O plus. Now, so everything so far is exactly the same to the last problems we were covering in the last video. We're going to set up the equilibrium constant expression, right? We know a couple things. We know that KEQ, right, is going to be equal to our concentration of H3O plus times the concentration of CH3COO minus, right, all over our concentration of CH3COOH. Now, we know that these x's can go in here. And this whole setup here can go down there. All right, so again, this is all still equivalent to what we covered last video, right? So I'm just going to erase this now so that we can kind of just use the... So all of that, right? We were given this value in the problem. Here's our setup, right? So at this point, we would normally solve the quadratic. Right? But here's where the 5% rule actually starts, right? So what the 5% rule states is that x, our change in our initial concentration, is less than 5% of the initial. Now, what we're really saying here is that this value here, this minus x, doesn't really change our initial concentration. Right, because if I subtract less than 5% of 0.1 molar from 0.1 molar, I'll effectively get 0.1 molar. So subtracting a number that is very, very small is really like not subtracting it at all, right, is our assumption. That this x value is so tiny that when we subtract it from our initial, we basically don't see much of a change in the initial concentration. Now, this rule or this assumption really only works when we have a really small equilibrium constant, like this one, 10 to the negative 5. It's a pretty dang small value, right? So the 5% rule is going to be usable here, but we always need to check to make sure we were within 5% of the initial concentration. Hence the name 5% rule, right? We're making the assumption that this value x is less than 5% of 0.1 in this example, or whatever else our initial concentrations are. So let's talk about this, right? So in order to simplify this from a quadratic equation to a simpler equation, we're going to assume x is very, very small in comparison to our initial concentration here. This means that it doesn't really change that concentration, and we can neglect that subtraction. So basically, we're getting rid of all that. This changes the problem from being a quadratic equation to just a simpler expression. It's not a quadratic anymore. So our equation effectively becomes x squared over 0.1 molar. This is a much easier equation to solve, right? We multiply both sides by 0.1 molar. And then to get rid of the squared, we square root both sides. And that's it. That's all we need to do here to solve this problem. So as you can see, it's much, much simpler to use the 5% rule. We can solve, we get x is 1.3 times 10 to the negative 3. Now, again, the 5% rule assumes that this value that we just assumed was less than 5% of our initial concentration, which in this problem was 0.1. Now, we always need to make sure that that assumption is valid. In other words, is correct. This value must actually be less than 5% of whatever your initial concentration is. Now, if it's not, then we need to start back over to this point, use that minus x, solve the quadratic equation as usual. So let's check. All right, so how do we tell if this value is less than 5% of 0.1? Well, we figure out what's 5% of 0.1 molar, which we can do by taking 0.05 and multiplying it by the initial. Or in other words, 0.05 times 0.1 gives me 5 times 10 to the negative 3. Now, is this value less than that? Absolutely it is. So yes, the assumption was valid. We can use the 5% rule in this problem. And it simplifies the calculations. Okay, so let's do another problem. So we're going to start dealing with problems that are a little bit more complex. So we have one last thing to deal with that we haven't seen yet in the last video or this video. And that is where you're given initial amounts of everything in the reaction, right? So in the past problems, we've always been given just the reactants and asked to solve for the equilibrium concentrations, or, initial and then one equilibrium. But in this problem, we're not given any equilibrium concentrations or pressures. We're just given initial pressures and the equilibrium constant. But in this case, we're given initial conditions for everything, all the products, all the reactants. And again, we're asked, what are the equilibrium pressures of PCl5, PCl3, and Cl2? This is a significantly harder problem. Let's see why. The next thing is to set up our ice table, right? We know we have 0.5 molar PCl5, we have 0.5 molar PCl3, and we have 0.6 molar Cl2. This was all given in the problem. But one thing that we've kind of taken for granted is because these have been always zeros, we've always put minus x on this side and plus x on this side. That's because the equilibrium was shifting toward the products. If there are zeros here, it can't shift towards the reactants. It has to shift towards the products. So, but in this scenario, which way is the equilibrium shifting? We don't technically know from what we were given. The equilibrium could shift either way. We need to figure out which way the equilibrium is shifting in order to get to equilibrium. And in order to do that, we need to calculate Q and compare it to K. Now, we were told that K is 0.497, right? So we know K, we need to calculate Q. And if we calculate Q, again, Q is using the initial concentrations or pressures and solving as though it was K. Well, that's products this times this over our reactants, that. Or in other words, 0.5 times 0.6 divided by 0.5. Now, if you get that value, you get 0.6 because, these two cancel and it's just equal to 0.6. Now, we need to compare Q to K and see which way it is, right? If they're equal, then we're at equilibrium, and these are equilibrium concentrations or pressures. If Q is less than K, then the reaction is going to shift towards the products. If Q is greater than K, as is the case here, then the reaction is actually shifting towards the reactants. Now, this means something very important. It doesn't change the values of X, but it does change the magnitude of X, but it does change the size of X. So instead of getting minus X on the reactant side, since we're shifting towards the reactants, we're actually producing more of them. In other words, this is plus X for the change here of PCl5. And the only way you would have known that is if you calculated Q and compared it to K. At this point, then we can go, okay, minus X for the products because we're shifting away from the product side, i.e. decreasing the products, increasing the reactants. And finally, we just add our two rows. And now we can solve our quadratic equation to solve for X. So, we can solve our quadratic. We got to set it up, right? We know Kp is equal to 0.497, and that's equal to 0.60 minus X times 0.50 minus X all over 0.50 plus X. Now, one of the things I see students doing every so often with problems like this is they go, oh, hey, 0.5 plus X those cancel with 0.5 minus X. And this is absolutely not true. So please make sure you do not do it. These do not cancel with each other. We need to solve this. It's a little bit more of a headache to rearrange this equation to solve the quadratic, but that's what we need to do. And so I'm going to let you guys do that work on your own and see if you get the same answer as me so that you can practice with the algebra. And if you have any questions, as always, discussion session or office hours. So we solve for X using our quadratic equation, right? What you're going to get is that X is equal to 0.0329. And so we can kind of plug that into our ICE table. Basically, this value 0.329 goes here, and there, and there, and we get this. We add our two rows, and we get these partial pressures for everything at equilibrium. All right, so let's do one more example problem like this, and then we'll call it a day. Okay, so here's another problem. We have a container. It has initial pressures of everything in the container. So the first step here is going to be setting up the ICE table, right? So we have ICE. We have a 0.621 ATMs of H2. We have 0.621 ATMs of I2, and we have 0.101 ATMs of HI. Now, because we have initials of everything, we need to first calculate Q, right? So Q is going to be equal to 0.101 ATMs, and again, don't forget the square because of the 2 there, divided by 0.621 ATMs for H2 times 0.621 ATMs for I2. This will give me a value of 0.026 5. All right, so now that we have this Q value, we can compare Q to K, right? So we know 4.76 times 10 to the negative 4, and we have Q, which is 0.265, or 0.0265. So this is our Q, this is our KP. Let's compare them. Which one's bigger? Well, Q is bigger. This tells me the reaction is definitely shifting towards the reactants, which tells me how my change works, right? So this is going to be plus x here, minus 2x. Remember, this 2 comes from this 2 here, and we cannot forget that. That's a common mistake. All right, so we can get the equilibrium row, 0.621 plus x, 0.621 plus x, 0.101 minus 2x. And we can set up our equilibrium expression, right? So we have 4.76 times 10 to the negative 4 is equal to 0.101 minus 2x over 0.621 plus x times 0.621 plus x. Now, one of the common mistakes I see students make is they set up it like this, and then they've forgotten something. And it's a very important thing. Again, this 2 here is so important. We need to square that whole situation there because of the 2. So this is my setup. Now, just due to kind of serendipity, I guess, if we rearrange this a little bit, we get 0.101 minus 2x quantity squared over 0.621 plus x also quantity squared. Now, this isn't like a general thing, but it is a mathematical shortcut here. You can solve the quadratic if you want, but there's a way around it here for this specific problem, and that's because of these 2's here. Because we have both of those squared, what we can do as a shortcut is square root both sides, and the square root's going to cancel those 2's. This will give me a value of 2.18 times 10 to the negative 2 is equal to 0.101 minus 2x over 0.621 plus x. Now I can multiply both sides by 0.621 plus x. This is no longer quadratic, by the way, on both sides. And this will give me a new expression, which I'm going to do over here. This will give me 0.0135 plus 2.18 times 10 to the negative 2x is equal to 0.101 minus 2x. So at this point, I can kind of continue to solve here. I'm going to add 2x over and subtract over the 0.0135. Just doing some algebra here, right? So I'm going to subtract 0.0135 here minus 0.0135 here. And I'm going to add 2x over here to both sides. This will give me a new expression, which will be 2.0218x is equal to 0.0875. And last but not least, I can solve for x. This will give me my final answer of x, at least for x, sorry, not my final answer, of 0.0433 atm. Now I'm not technically done here. I need to take this value and plug it in. Now I'm going to erase some stuff to give myself some room to do that. Just 1 second. Okay, so let's just kind of erase all these guys, and then we'll just replant into our whole situation here. So we have plus x, so 0.0433 here, there, and minus 2 times 0.0433 there. So this gives me 0.0664 here. Oh, sorry, not 0.664. And the same thing here. And then these are in the ATMs. And then, and 0.0144 ATMs of HI. All right, so that should be our answers because we were asked for this value here, which is our correct answer. All right, so if you have any questions, please let me know. This is the end of chapter 15. Discussion session. We'll probably have our exam review coming soon. If you have any questions, email me, come to discussion sessions, come to the exam review. All right, have a good day.